I want to start part 4 here of chapter 14 by saying this video is going to cover some of the nuances of NMR, that's proton NMR specifically, and some more subtleties. I want to emphasize the importance specifically for my class of the first 3 videos and making sure you're good with all of those foundational ideas, right? Integration and splitting and where the peaks are appearing. That's really the big part of proton NMR. And here we'll talk about some other information that we can get from those spectra. And continuing on from where we left off in video 3 with that bromopropene spectrum. Yep. And the actual shape of these peaks for high-res NMR is notable. Yep. Because if we've got 4 peaks, for example, here, it gives us different information if it's a quartet, which maintains that 1:3 to 3:1 ratio we introduced previously, versus a doublet of doublets, which has 4 peaks all the same height. You see the ratio there. So a quartet is from 3 equivalent adjacent protons, whereas a doublet of doublets is due to splitting by 2 non-equivalent protons. So it's, one proton splits it once into 2 peaks, and then the other non-equivalent proton splits it again, each of those 2 peaks again, so a total of 4. So this is 3 neighboring protons splitting simultaneously. A doublet of doublets is from 2 non-equivalent protons. But you have to have high-res blown up peaks here to actually see the differences. But just be aware that they are different. The other tricky thing we sometimes have to worry about is aromatics, benzene rings, things like that. Like, look at ethylbenzene here. Now, we would anticipate 5 unique signals. But the challenge is that for the protons on the ring here, you have C, D, and E, the ones that are further upfield here, or sorry, downfield, they overlap one another. So we get really just one messy multiplet over here. The resolution of this spectrum is not high enough to actually separate these things out. So the aromatic region of these NMR spectrums can really be dicey, unless you have something incredibly high res. Okay, because even though we have 5 chemically unique protons here, we only see 3 signals here. The integration still helps us, right? But actually seeing these things can be challenging unless you've got a strong enough group on benzene. Okay, so here you see the electronic effect of the ethyl substituent, too similar to that of hydrogen to separate those guys out. But if we change the group here and look at nitrobenzene, for example, now we have a stronger electronic effect because that nitro group is more electron withdrawing. So now for the 3 different protons we have, we do actually see those peaks be unique. We can see them. They've been resolved on the spectrum. They're not overlapping one another. So we get signals for each, right? A doublet, a triplet, and then all the way on the right over here, a doublet of doublets, okay? Because A is being split by 2 non-equivalent protons, which we started the video with. And the specific way that these things split does give us some valuable information. We can get a lot, right? We talked about mutual coupling, right? And we can figure out what protons are splitting one another by using something known as the coupling constant, which is represented by J. Okay? And the coupling constant is the distance between 2 adjacent peaks of a split signal. Okay, it has to be split in order to, anything that's coupled will be split. And the difference between those 2, right, measured in hertz, with our value, that will tell us things that are paired, right? So we have J for the coupling constant, JBA and JAB. We use that notation, right? Those subscripts, the 2 things that are splitting one another. It's really useful in busy spectra because we've got protons on adjacent carbons, and we can identify what are splitting one another by identical coupling constants. The value is the same for JBA in JAV, right? If we had JAC, it would be the same value as JCA. And they're the same value regardless of the operating frequency, right? That's the good part of NMR. The magnitude of the J value, right, is a measure of how strongly the two nuclear spins of the coupled protons are influencing one another, right, which depends on a variety of factors, the number of bonds, the type of bonds, the geometry. Okay? But coupling constant is a really valuable tool. I wouldn't expect you to know coupling constants, so don't worry about memorizing the information from table 14.2 here. Okay? I just want you to be aware of the concept, right? That the coupling constant, the value, the distance between the peaks is the same. Right? That's what we're seeing here. That's how we identify protons that are coupled to one another. And that's valuable because it can do things like distinguish if we've got cis or trans isomers. Okay? The coupling constant is greatest when the bond angle is 180 degrees. Okay? So the coupling constant is the greatest value for trans isomers versus cis isomers. See the difference? 14 hertz versus 9 hertz. That's really valuable information that we can get, right? Because this is the only way, using the different techniques we've talked about, to differentiate those things. Okay. So, right, that's just another use. Have it on your radar. Coupling constant, valuable info. Okay. So to summarize what we've seen so far in the chapter, right? However many unique protons we have, right? That's how many signals we get. The number of signals tells us the number of sets of equivalent protons, right? The value of the shifts in ppm tells us about what kind of environment we are. Integration tells us the simplest ratio, the relative number. Splitting tells us about the number of neighboring protons, right? Singlet, doublet, triplet, etc. And the coupling constants can then take it one step further and identify the protons that are coupled with one another and causing that splitting phenomenon. But what about if a signal is split by more than one set of protons? That can kind of throw a wrench into things too, which is what 14.14 is about. Okay? Splitting diagrams and multiplicity, which is the bulk of this video, kind of, taking the oversimplification from before. And now we're thinking about being split by non-identical protons, elaborating on that a little bit further. Okay, so when we have a doublet of doublets, this is now a really useful diagram to see what's going on. And this is known as a splitting diagram or a splitting tree. This is depicting the splitting of proton C right here. So if we look at its neighbors, it's got a proton over here and then a proton over here. Okay? So we think about it first being split by the B proton. Again, it can be with the magnetic field or against, but with and against. And that splits us into a doublet, just looking at the effect from B. Then the effect from D, right, splits it again. So we go from a singlet, one signal, to a doublet, and then split that doublet again. Now we get a doublet of doublets. Okay. So for multiplets, what's going on there? Well, and this is not something I would expect you to do, but just be aware of the fact that, these multiplets, it's not like we just go above 4 peaks and throw it out the window and don't worry about it, right? How many peaks in the multiplet gives us some good information as well. It depends on the relative magnitudes of the coupling constants too, right? Because that dictates how many overlap, right? If they overlap, then the intensities add to one another. So if we have two coupling constants that are identical, right? Looking at B here, right? B is going to be split by both A and C. Looking at the effect of splitting from A first, that would take us into, right, a quintet, 4 signals. And then if the coupling constants are the same, right, then we just, right, have the effect of splitting by C. And these things you can see start to add to one another. So even though every peak is being split into 2, we don't go from, right, the 4 here into more. We get 6 peaks because you can see where they've all overlapped from one another. And if you have your coupling constant that's exactly double, you can get 9 peaks. Okay? Or if the coupling constants are notably different, then you can get up to 12 peaks. Okay? So again, just information that can come out of a multiplet, which is why sometimes if we're looking at the resolution of these things, right, we would normally expect 9 peaks, but we only see a quintet rather than a multiplet because the coupling constants for JBA and JBC are identical, which again leads to exactly 6 peaks. Okay. So what does it come down to? Again, most of the examples we're going to see are the earlier ones. But what it boils down to, if we've got 2 different sets of protons splitting a signal, we can use the n+1 rule separately. If the coupling constants are different, we can use it simultaneously if the coupling constants are the same or very similar to one another, right? So it's either do you split it twice, so do n+1, split it once, and then split it again, like the doublet of doublets, or if the coupling constants are the same, you can do it all at once. And so the difference is, right, doublet of doublets here, it's the n+1 rule. You do it twice. So you do it once to get a doublet, and then you do it again to get a doublet of doublets. If the coupling constants were the same, right, then you take each of those protons, 2 + 1, and you would assume it to be a triplet if the coupling constants are the same. Yeah. It's complex, right? But just stuff to have on your radar about multiplets. I'm also going to skip 14.15 completely, right? It's a little, it's even more advanced than this. It talks about enantiotopic and diastereotopic hydrogens and prochiral carbons. Those do have their roles in NMR, right? But as I said, they're a little tricky. All I want you to know is that enantiotopic hydrogens are chemically equivalent, so we wouldn't see splitting by those, but diastereotopic hydrogens are not. Okay? They are chemically distinguishable. What else? What other things do we have to look at? Right? Well, if you think about all the way back to your Newman projections, right? We've got things that are anti or gauche or eclipsed. We could think about those as being chemically different too, right? However, keep in mind that that bond between those 2 carbons is freely rotating, and it rotates fast, right? So by the time we could acquire an NMR, we can't distinguish between those 2. It's happening too fast. Anything that interchanges in less than a second cannot be distinguished by NMR. Okay, so you cannot tell the difference between these with NMR. Ring flip would be another example, right? We talked about cyclohexane and how it can do a ring flip. It's happening too fast. You can't tell the difference between axial and equatorial, for example, in NMR. Okay, which is good. So how could we, if we wanted to, actually distinguish these 2? Well, we have to stop the ring flip, okay? Because if I've got cyclohexane in room temperature, it's going to just show 1 signal, as I just mentioned. But if I can slow or almost stop the ring flip, then I can distinguish the difference, okay? It does take energy. There's an energy barrier to do this ring flip, okay? And usually room temperature is good enough to overcome that. Well, it always is, right? But if we decrease the temperature, then the signal broadens, and eventually, as you get cold enough, -89 here, you do get 2 signals because you've cooled it, you've removed the energy necessary to do the ring flip, and now those are in different environments. Okay, so that's pretty neat. Not, just a fun fact for you. So we finished the video by considering protons that aren't bonded to carbon, because that's all we've been talking about so far. So what goes on? What if we have a proton bonded to oxygen or to nitrogen? Well, the signal location varies with the degree of hydrogen bonding. Okay? More hydrogen bonding means we have a larger shift due to decreased electron density. Okay? So we see ethanol, and then here's ethanol with a little bit of acid. Okay? So what's the difference here? Ethanol and then ethanol with acid. Ethanol, okay? Ethanol with acid. What do you see as the difference? Right? Look at that peak that's further downfield, okay? Around 5, and what's going on. This is the proton spectrum for ethanol that we usually see. Okay? And note for the signal for the proton here that's bonded to oxygen, that's this proton right here, that's appearing above 5, the one for this downfield. It's not split. Okay? It's also not splitting the methylene signal over here. Okay? And the reason for that is that it's undergoing proton exchange. So again, if we, looking at this hydrogen, which is this peak, appearing as a singlet, not split, but there are 2 hydrogens over here. So we would anticipate it to be a triplet, right? Like we see over here for pure ethanol. And again, over here, that's corresponding to these methylene protons, that's just appearing as a quartet, okay, being split by these 3 hydrogens. Whereas normally we would anticipate a multiplet, like we see right here. So why, when we add a little bit of acid, do these things not split one another? This would be the B protons, this would be the C protons. So why are they not splitting one another? Well, when we have protons bonded to oxygen or nitrogen, we frequently have proton exchange in the presence of that acid, acid-catalyzed proton exchange, where protons are being readily transferred from one molecule to another. In order for NMR signals to split one another, the proton has to stay attached for a notable amount of time. In proton exchange, right, these things are not doing that. Okay? The chemical shift depends on the extent of hydrogen bonding. And you see these protons, right? Look at this, it's the yellow to begin with, and then I protonate my alcohol, and then I lose the original proton. So these protons are just kind of going in and out, in and out, in and out. Okay? They're not staying bonded long enough to split the signal. And in a pure alcohol, pure ethanol, right, jumping back 2 slides, this is a slow process, and that hydrogen does stay bonded there long enough to split the signal. But when we catalyze it with an acid, it happens much faster. At bases, even trace amounts of acids and bases catalyze that proton exchange process. Yep. And because our spectrum is an average of all the possible situations, that rapid exchange produces a broad singlet. Yep. So we doesn't get split by anybody else, and it appears a little bit broader. Yep. They don't give very nice peaks in NMR. Okay. Looking at this, that's the best case scenario. Usually they don't look that good. And if you ever think you have something that's undergoing hydrogen bonding, you can confirm that by checking it with deuterium, okay? Which is what this is saying right here. An OH signal or an NH signal can be identified by taking the spectrum by adding D2O. It's known as heavy water, right? Deuterium oxide. Remember, deuterium is the heavy isotope of hydrogen, the neutron. If you put your alcohol in with deuterium, right, it'll undergo proton exchange. It'll pick up a deuterium, and deuterium is not seen in NMR. Okay? It's not NMR active, so your peak decreases in intensity. So what do we, oh, I thought there was an example right there, but there's not. Okay, so effectively what you would do, going back some slides here, you think this is corresponding to an OH. So what do? You put your solution in with D2O, you see that peak go down, now you've confirmed what's going on. Okay? And deuterium is also really useful for NMR solvents, right? D2O itself is a pretty common NMR solvent, so is deuterated chloroform, CdCl3. Okay. So we finished with a quick discussion on the instruments themselves. If you're trying to get a really clean splitting pattern, the difference in the chemical shifts of coupled protons have to be at least 10 times the value of J. Okay. Otherwise, your peaks are going to start to run on top of one another. And that's where higher resolution instruments come into play. But of course, they're more expensive. That's the challenge. But you can see how much cleaner these get comparing 60 versus 300. Okay. Right, I told you about the ratio before, 10 times the value of the coupling constant in order to get a nice clean peak. Keeping in mind, differences in chemical shift, right? The ppm value will vary in megahertz depending on the NMR used. Okay? We're still going to get them at the same peak. That's the beauty of the ppm system from a previous video. But the J values stay the same no matter what. So again, this is probably a confusing video. It might take another watch through to get the hand on what's going on here. The big takeaway, if I had to pick one thing, the coupling constant. Okay? Know that we can identify coupled protons because they have the same value of the coupling constant. Know whether or not you can use the n+1 rule, but this is, advanced NMR stuff here in video 4. I want to strongly emphasize the material that's introduced in the first 3 videos, then pick up this stuff later on. We'll finish in our final video, part 5 of chapter 14 with NMR for things other than protons. Because everything in these first 75 slides and 4 videos has been proton NMR, but as we mentioned in the first video, there are other types of NMR as well.